Continuous annuities. A continuous annuity is one in which payments keep happening continuously instead of happening a certain number of times a year. So note that the overall term of the annuity is still finite, but during this finite term, payments happen continuously. So let's consider the following cases, and we need to know different formulas for these different cases. Case one, constant continuous payment rate and constant effective interest rate. So you know that mostly we have been dealing with constant effective interest rate, but sometimes we do deal with variable rate like the variable force of interest. So constant case one is constant continuous payment rate and constant effective interest rate. So consider a continuous annuity for n years such that the total amount paid each year is 1. So again, the total amount in the year is 1, but now instead of happening it at a fixed time during the year, usually we've dealt with payments happening at the beginning of a year or at the end of a year. Or like, for example, if there are quarterly payments, they happen at 4 different spots during the year. But this time, the payment is happening throughout the year, or it's spread uniformly throughout the year. And the total payment in the year is 1. And suppose we have the usual compound interest, that is what we can also call as constant annual effective interest rate. That's the usual compound interest. So the present value of this annuity is given by, so this is the notation, AN. Remember, AN was for the annuity immediate, where payments are 1. That was the present value for annuity immediate. But if you put this little bar over here, then it means that the payment of 1 is not happening at a particular time in the year, but it's spread out throughout the year. So the formula for the present value is 1 minus nu to the n over delta. And we already know what these mean. Delta is the force of interest, the constant force of interest that corresponds to the constant annual effective rate. And we know that delta is equal to ln 1 plus I. And nu is a discount factor that we've seen so many times before. So 1 over 1 plus I. And another way of expressing this is all in terms of delta. So if you express everything in terms of delta, then it becomes 1 minus e to the negative n delta over delta. And now, if the total payment during each year, instead of being 1, if the total payment per year is x, then as usual, we just multiply this present value by x. And similarly, in this other equation, we multiply this value by x. So this was the case of constant continuous payment rate and constant effective interest rate. Now in case 2, we still have constant continuous payment rate, but now we have variable force of interest. So the interest rate is no longer constant, but variable. And in this case, again, we consider a continuous annuity for n years such that the total amount paid each year is x, spread continuously. So here I'm not treating the payment of 1 separately, because if I treat the total payment of x, then payment of 1 is just a special case of it where x is equal to 1. So if the total payment each year is x, and it's again not happening at a particular time in the year, but spread continuously throughout the year, and the force of interest is variable, let's say delta t, then the present value of this one is x times integral 0 to n, where n is the total number of years for which the annuity happens. So then we have e power negative, and again, integral in the power 0 to t delta r dr. And now case 3 is when we have variable continuous payment rate and variable force of interest. So now both are variable. The payment rate is variable and the interest rate is variable. And again, we consider an annuity for a duration of n years, but now the payment rate per year is f of t. And instead of being constant throughout the year. So if the variable force of interest is delta t, the present value in this case is the integral from 0 to n f of t e power minus 0 to t delta r dr dt. So you see this case 2 is a special case of case 3. If the payment rate, instead of being f of t, a variable payment rate, if it's just constant and it's x per year, then you just replace f of t by x and you get 93.5. And then case 4 is we have variable continuous payment rate, but constant annual effective rate. So again, consider an n-year annuity. The payment rate is variable. Let's say it's f of t per year. And suppose the annual effective rate is now constant. So in this case, the present value is f of t nu power t dt, and the integral of that from 0 to n. And again, note that these integrals that appear in cases 2, 3, and 4, the main integrals, the outside integrals, they are starting at 0 because usually we consider in continuous annuities, we consider an annuity which starts its payment right now. But there are situations where the payment doesn't start, even though it's continuous, but it doesn't start right away. It starts at a particular time, at a later time. Then if the starting point of the payment instead of being 0 is C, then we integrate not from 0 to n, but from C to C plus n. If the duration, where n is the term of the annuity duration. So if it continues for n years, for example, and it starts happening at time C, then the integral goes from C to C plus n. And I've just illustrated it for this case 4, but the same thing happens in cases 2 and 3 as well. And again, if we deal with a constant force of interest, so here I've expressed this present value in terms of mu, which we mostly remember as 1 over 1 plus I. And I is the annual effective interest rate. But if you want to express it in terms of delta, which is the constant force of interest, then the integral takes this form. So let's understand these formulas. We have quite a few formulas here. So let's understand them through examples. Example 93.1. Find the accumulated value after 5 years of an annuity with continuous payments of 100 per year if the annual effective interest rate is 6%. So you can see here that the payments are 100 per year, so it's a constant payment rate, and the effective interest rate is also constant. So this is case 1. So remember, in case 1, the formula for the present value is x times 1 minus nu to the n over delta, where x is the total payment in the year. So here we are having a payment of 100 per year. So x will be 100 in this case. Delta will be ln 1 plus I, and I is 6%. I is the annual effective rate. So the equation becomes x, which is 100, times 1 minus mu to the n, so 1 minus 1.06 to the negative 5. It's a 5-year annuity, over ln of delta, and delta is 1 plus ln of 1 plus I, delta is ln 1 plus I. So this present value comes out to be 433.75. And I just gave you the present value formulas because the accumulated value can always be found by pushing the present value to wherever you want to accumulate. So in this case, we want the accumulated value at the end of 5 years. So present value right now is 433.75. So you push it forward through 1 plus I to the 5, multiply the present value by 1 plus I to the 5 to get the accumulated value at time 5. And I was 6%. So we get 580, and that was choice E here. Example 93.2. Find the present value of an annuity with continuous payments of 10 per year for 8 years if delta t is 2 over 1 plus t. So you see that the payment rate is constant, 10 per year, but the interest rate is variable. So this is case 2. And in case 2, we saw the present value formula was x times the integral 0 to n of e power negative 0 to t of the force of interest. And x was the payment per year, the constant payment per year, which in this case is 10. And the integral will be from 0 to 8 because it's 8-year annuity and it starts right now. And integral e power. So first integral is 0 to 8, and then we have e power negative 0 to t, 2 power 2 over 1 plus r, because delta t is 2 over 1 plus t. So delta r will be 2 over 1 plus r dr. And the integral of 1 over 1 plus r is ln 1 plus r, and we have a 2 outside, and we have a negative sign, so it will be negative 2 ln 1 plus r. And then so here I think I've just rewritten this step again. So I can erase that. Okay. So when I substitute t, I get negative 2 ln 1 plus t. And when I substitute 0, it's ln 1 plus 0, which is ln 1, and ln 1 is 0. So when I put in the lower limit, the ln 1 is 0, so it goes away. And we just have negative 2 ln 1 plus t. And then when we raise this negative 2 to the power of log, which we can do, you know that this coefficient of log can move around in the power, and that this is a log property that we learned in pre-calculus. So this is equal to e to the ln 1 plus t whole power negative 2. And we know that when e and ln are together, in one is in the base, one is in the power, they cancel out. So it's just 1 plus t to the negative 2. And since it's even power, so we can get rid of the absolute value. And the integral of 1 plus t to the negative 2 will be 1 plus t to the negative 1 over negative 1 if we use the power rule. And then when we substitute 8, this is 9 power negative 1. And we have a negative outside. So negative 10 outside. So 9 to the negative 1 minus, and when you substitute t equals 0, you get 1 power negative 1, and all this simplifies to 8.89. And that was, that will be rounded to choice D because all of the choices are rounded to integers. So 8.89 rounds to 9. And next few lessons will be about the SOA problems of continuous annuities. So stay tuned.